Hi everyone, I wanted to provide video solutions for today. So for number 36, the problem states, if V1 to V4 are in R4 and V3 is not a linear combination of V1, V2, and V4, then the set V1 through V4 is linearly independent. So I'm going to provide a counterexample here. So I'm going to let V1 be the vector 1, 0, 0, 0. I'm going to let V2 be the vector 0, 2, 0, 0, 0. I'm going to let V3 be the vector 0, 0, 0, 1. I'm going to let V4 be the vector 3, 0, 0, 0. So notice that V1, V2, and V4 are all scalar multiples of each other. So the set V1 to V1, V2, V4 is linearly dependent, and V3 is not a linear combination of the others, right? We would not be able to write V3 in terms of V1, V2, and V4 because they only have non-zero numbers in their first element. But my counterexample is that this new set, V1, V2, V3, V4, is linearly dependent. So I've shown that the initial condition holds. You've got 4 vectors in R4, with V3 not being a linear combination of the other 3 vectors, but the set of all 4 vectors is linearly dependent. So that is false, and that's my counterexample. So this is false. Okay, so for 37, the problem states, if V1 to V4 are in R4, and V1, V2, V3 is linearly dependent, then V1, V2, V3, V4 is also linearly dependent. So here's my explanation here. If the set of 3 is linearly dependent, that means that there exist scalars, not all 0, such that this is true. So this means that at least one of those scalars is not 0, right? Well, now let's add so maybe let me note that. So at least one is not 0. Okay, so if we add a 4th vector into the set, now we have C1 V1 plus C2 V2 plus C3 V3 plus C4 V4 equals 0. Because we already know that there's a linear dependence relation among these, this last one may be a linear combination of the others, or it may not, but who cares? Even if C4 is 0, right? Even if C4 is 0, we still have a linear dependence relation because we still have scalars we can put on V1, V2, and V3 to reach the 0 vector. Okay, so this statement is true. This statement is true. For number 38, it says, if V1 to V4 are linearly independent vectors in R4, then V1 to V3 is also linearly independent. Think about x1 V1 plus x2 V2 plus x3 V3 plus 0 V4 equals 0. Right, so let's see, if you have a set of linearly independent vectors, that means that the only solution, so this is a true statement. If these 4 vectors are linearly independent, let's do it with a matrix actually. So let's think about 4 vectors, we put them in a matrix, right? And they're linearly independent, which means we're going to have 1s on the diagonal here, right? Because in order for the set to be linearly independent, we have to have a pivot position in every column, right? We have to have no free variables when we go to solve AX equals 0, right? Like this is A, X is our matrix, which would contain the scalars, and then this is our 0 vector, right? So if we eliminate V4, okay, so if we dump this, then we have a new matrix that's 1, 0, 0, 0, 0, 1, 0, 0. We know it's going to ref to this. And we still have a pivot in every column. We don't have a pivot in every row anymore, so we wouldn't be able to span all of our 4, but we still have a linearly independent set. That one is true. Okay, and then for my last case, for number 41, we've got a matrix A. We're supposed to use as many columns of A as possible to construct a matrix B with the property that the equation Bx equals 0 has only the trivial solution. So this thing should only have the solution that's the 0 vector, which means we need the vectors to be linearly independent. And so currently we have a set of 5 vectors in R4. So we know that that's linearly dependent. We're trying to figure out, I'm going to paste in the ref form. So I already did that on the calculator. So here's the ref form. So let's write this out in parametric vector form. So x1 equals, let's see, there's 5 vectors here, aren't there? So x1 equals negative x4 minus 3x3. x2 equals negative 5x4 minus 8x3. And we have x5 equals 0. Oh, I probably should put those other 2 in there. Hang on. So we'd say x3 is x3, and x4 equals x4, but x5 equals 0. Probably would have been helpful, actually, for me to augment this with zeros. Helpful in writing the solution. So in parametric vector form, we could see that this would be, the set of solutions would be x4 times -1, -5, 0, 1, 0, plus x3 times -3, -8, 1, 0, 0. So let's think about this. One linear dependence relation among the columns would be negative A1 minus 5 A2 plus A4 equals 0. And another one would be negative 3A1 minus 8A2 plus A3 equals 0. So this shows us that A5 cannot be written as a linear combination of the others, but A4 can be, A3 can be, A2 can be, and A1 can be. Okay, so A5 is absolutely essential. A5 is needed. Okay, we're going to use as many columns of A as possible. Okay, so A5 is needed, but we can get rid of, let's see, any 1 or any 2 of the remaining. So let's think about this. So if we axed A1, would we still, so I'm going to delete A1. Okay, and I'm going to ref. Okay, so getting rid of A1, there's still a free variable, isn't there? So we don't have this working. So I think we need to get rid of 2 vectors, right? I think we need to get rid of A1 and A2, let's say. Oops, sorry. Let's get rid of A2, which is now the first vector in the spot in the matrix. Okay, there we go. Okay, so this now has the property. So what we'd want to do, we would want to eliminate the first 2 and just leave us with the vectors, the 3rd vector, the 4th vector, and the 5th vector. Okay, so we would construct B by taking A3, A4, and A5. Then you have a linearly independent set.